The following video recording has been made possible by Symbotic, complete warehouse automation. From integrated supply chain consulting to fully automated picking systems with progressive financial models. Symbotic systems are deployed in major grocery, retail, and general merchandise operations throughout North America. Learn more at Symbotic.com. And by Duchin Productions, broadcast, corporate, and web video production services specializing in science and technology. Start the conversation today. Visit DuchinProductions.com to learn how video can get your business the customers, talent, and investors you've been looking for.
I'm going to tell you about our work over a number of years in trying to build robot hands that are actually useful in the real world. And the challenge with the real world, with unstructured environments, is all the variations that are present there. So take a very simple task, picking up a coffee cup from a somewhat cluttered desk. And there's a lot of variability you have to deal with. The object size, shape, and so on aren't really very well known, and your sensing isn't going to give you an exact picture of that. And the result is, when you command your big robot arm to come in and try to pick up that hand, you'll get a lot of contacts you weren't planning, and some you were planning don't happen. And the result is, you can knock over the object, you can damage the object, you can damage the hand. And so dealing with that variability is really key. Now, of course, people have been trying to build robot hands to deal with this for many years. The usual approach has been anthropomorphic. We don't know how to build a good robot hand, but hey, that thing on the end of my arm works pretty well. I'll just build one of those. And as you can see, for years we've done a great job of capturing the kinematics, the structure of the hand. The controls haven't been quite so easy. So you can see here that every single move of that robot hand is actually commanded by the human operator. And so autonomy just isn't there. So we decided to try a very different approach. Instead of aiming for human-level manipulation, which is kind of trying to run before you can walk, we said, let's try going the other way. Let's try to make a very simple system where we have a minimum number of motors and sensors, but we'll try to use passive mechanics, both in the hand design and the way it interacts with the world. And the other important realization is that you got to deal with crashes. They're going to happen, and you better make sure your hand doesn't break, or your graduate students will be very reluctant to use it in real experiments. So this is sort of the end of the first set of design experiments we tried. And if you can kill the sound, please. There's no sound on this. Really get in the way. Okay, I'll just talk over it, sorry. Anyway, the idea here is we built fingers that are flexible and have rubber flexures instead of ball bearings and metal shafts. The result is they adapt to the object shape. The other thing we did, you see in the lower picture, is we have this adaptive transmission. There's really only one motor that's pulling a cable to close the fingers. But if something stops one of the fingers from moving, the others just keep right on closing. So this allows passive adaptation without the need for sensing. So this is some video of adapting to various object shapes. By the way, you should never believe a hand is good, because when you put objects in it, it grasps well. It's the other way when the hand goes to the object that you can tell if the hand works well. But you can see how the adaptation works. Even when it's a three-dimensional object, something curved, the fingers just wrap right around it. Oops, sorry, getting ahead of myself there. There we go. So then we went on, and that was the sort of proof of concept of this approach of using well-designed mechanics, both in the finger structure and in the drive system, enables this automatic adaptation to the uncertainties of the real world. We then went on to build a hand that could move beyond the kind of power grasps you saw with that last hand, one that's able to do a much broader range of grasping manipulation tasks. This is a project we worked on with iRobot and Yale. And this hand has the same flexures in the fingertips you saw in the other one, but it also has the ability to change the finger orientation. So you can see here those spin around. That means you can move the fingers into opposition to do pinch grasps for very small objects, as well as wrap grasps for larger objects. We didn't lose sight of robustness. This is out behind iRobot one day, where we created the world's most expensive batting tee. And you can see in the slow-mo here that the fingers really take a whacking. They really go flying. And nonetheless, they continue to function at the end of that. So I think we can claim we've solved the robustness issues. And again, some tasks. This is palming a basketball, something I wish I could do. It's about a 250 millimeter diameter sphere, and this is picking up a 2.5 millimeter diameter sphere, so that's about 100 to 1 size range. And this is picking up flat objects. There are little fingernails on the fingers, which is kind of a cute trick for picking up flat things. But what really makes this hand work well for this is the fact that the fingers are flexible and compliant, so you just jam the hand down against the surface, close the fingers, and off they go. You don't have to precisely control the relationship of the hand to the surface. Okay, so we finally have a hand that's good for the real world. And programming up a mobile manipulation system that you can take out into the real world and test is quite a big deal. So we thought we could shortcut by putting the hand onto a handheld hand, sort of a rig, and taking it out in the real world. Here we are out at the Haymarket greengrocer. And we learned a couple of things from doing this. One is that if you walk around with a robot hand in Boston, everyone assumes you're from MIT. The other thing we learned is, in fact, the information you gain from positioning the hand in space is absolutely essential to understanding how to interpret what the fingers are doing and what contact sensor signals are telling you. So while this was a lot of fun, in fact, you don't learn that much from it. But let me go on and talk about some of the applications we're looking at here. So this is a set of where I think some real leverage for this kind of an adaptable hand lies. And it starts from things like warehouse and distribution systems, where there's some variability in the objects you deal with. It isn't quite as repeatable as, say, a welding robot in an auto factory where they execute the same task again and again and again. Here there's some range of objects, but you know what that range is because they're your objects and you put them through the system. Things start to get more complicated when you start looking at packaging items, doing flexible manufacturing, and then I think the sort of grand challenge is household assistance, which is extremely challenging for some reasons I'll mention. But let me first talk a little about e-commerce order fulfillment. What's that?
There might be controls on there.
Yeah, we tried.
On your laptop?
It doesn't work. It doesn't work. Let's see. Anyway, so Kiva, or now Amazon Robotics, has greatly automated the distribution centers, and the way they've done this is by moving the goods to the picker. It used to be people pushed carts up and down the aisles. That took about 2/3 of their time. Now the robot brings the carts to the person, but the person has to do the picking. That last little step from the shelf to the box is still manual. So this is a situation where a hand like ours could be quite useful because it can handle a wide range of objects. Down at the bottom, you'll see one of the prototype systems from a spin-off from our lab, Right Hand Robotics, picking produce. I think those are actually red onions, and putting them into boxes. So there the variability is too broad for most robot hands, but it's simple enough that current technology might be able to actually make it work commercially. Now, reliability turns out to be the real bugaboo in a lot of this, as with a lot of autonomy and robotics. For instance, self-driving cars. We all hear a lot about the lack of reliability of self-driving cars these days. In e-commerce, this number is kind of shockingly high. They're kind of aiming at the 1 in 10,000 error level for shipped boxes. Now, the good news is that doesn't mean that all the picking has to have that low an error rate. It means you have to have methods for detecting and correcting errors. Nonetheless, it's still a major challenge. And again, the grand challenge might be in the kitchen. And if you think about grandma having trouble dealing with taking care of herself in the kitchen, you want to hire a robot to help. Well, if your robot is 99.9% successful at grasping, this means it's going to drop something about every 2 days. So grandma is now cleaning up after the robot, and you're not going to have that robot around for very long. So an interesting question is, how many drops can you tolerate? And I'm guessing something like once a year. You clean up after a robot once a year and not think it's a complete waste of money. So that's an extremely high bar for us to work on for robotic grasping. So let me summarize then. We think that variation is a central challenge in the real world, both variation in your sensing and variation in the objects and situations you have to deal with. But there's some good evidence now that passive mechanics can do as much for you as active sensing and control, and it's a heck of a lot easier to build and implement. At the end of the day, though, reliability may be the real limit here, and that's going to be a very complex problem to solve that'll involve both the kind of systems I've been talking about, as well as the meta systems, the pieces around it that do the error detection and recovery before problems really occur. And validating that performance is tough, so figuring out how to prove something only makes a mistake once a year is going to take many years of data. We'll see how that goes. So these are the people who did the real work I'm taking credit for, and thank you for your attention.